You ever look at software development and feel like it's, I don't know, like assembling something incredibly complex with instructions that are just diagrams? You get the pieces, the code, the features, but making it all work together smoothly, that feels like the real
Oh,
challenge.
absolutely. It's a world of interconnected parts, layers
Okay.
upon layers. You really need a structured way to visualize it all, to manage that complexity. It's pretty essential, really.
Yeah, well, which brings us nicely to today's deep dive. One of you, working as a product manager and wanting to, get a better handle on the dev team's world, sent us a really comprehensive source.
Right.
It's Software Modeling and Design, UML, Use Cases, Patterns, and Software Architectures by Hassan Goma. I mean, this thing is massive. It covers everything from the basic drawing conventions right up to, well, entire architectural blueprints.
It's definitely thorough.
So our mission today is basically to give you a shortcut. We're going to pull out the core ideas, the fundamentals of modeling and design from this book. Focus on what's practical, what gives you, the listener, real value without getting totally swamped in detail.
Exactly. The book covers so much ground, notations, architectures, everything. We want to distill those key principles that connect it all, give you that solid foundation for understanding how these systems are actually thought out and put together.
Okay, let's start unpacking it. The book kicks off with how we even describe software designs. It talks about software design notation. What's the essence of that?
Well, think of it as your communication toolkit for software ideas. It's about having ways to describe these designs clearly, sometimes visually, with diagrams, sometimes textually, maybe like very precise instructions, or pseudocode.
Both.
Or often a mix of both, yeah. The main thing is having a clear, unambiguous way to show the software structure and how it's supposed to behave.
And the source puts a lot of weight on UML, the Unified Modeling Language. Why is UML so important here?
UML is, well, it's basically the standard visual language for modeling object-oriented stuff. And what's really key is that it's methodology independent,
Meaning?
meaning it doesn't matter how your team builds software, which process they follow. They can still use UML to draw consistent, understandable pictures of it. It's like a common blueprint language that different builders can all understand, even if they hammer nails slightly differently.
Got it. A universal blueprint language. The book lists quite a few UML diagrams. Can you give us a quick rundown of the main ones?
Sure. The source hits the key ones. First, you've got use case diagrams. Think of these as capturing the user's perspective. What does the system need to do for the people using it?
Okay. Yeah, what it does.
Exactly.
Yeah.
Then class diagrams. These are fundamental. They show the static structure, the different kinds of things in the system, the classes, their properties or attributes, and crucially, how they relate to each other.
Relationships like.
Well, like an order class being linked or associated with a customer class. And these links can get specific. You have whole part relationships like composition, where a car is made of wheels,
Yeah.
really strong physical link, or aggregation, which is weaker. Maybe a department has employees, but the employees can exist outside the department.
Right.
And you also have generalization specialization, which is basically inheritance, like saying a savings account is a kind of bank account.
Okay. Use cases for the what? Class diagrams for the what it's made of and how it connects. What else?
Then we move to interaction diagrams. These show how the different objects, the actual instances, work together to get things done. There are two main flavors here.
Okay.
Communication diagrams focus on the links between objects and the messages they pass, sort of like a network map. Sequence diagrams focus on the timing, showing the messages exchanged back and forth over time, like a script.
So who talks to whom versus the actual conversation flow over time?
Precisely. Then there are state machine diagrams, or state charts. These model how a single object changes its behavior, its state, over its lifetime based on events happening.
Like a traffic light changing state.
Exactly like that.
Yeah.
Green state, yellow state, red state, triggered by timers or sensors. Finally, the book mentions packages. These are just like folders, ways to organize all your diagrams and model elements to keep things tidy, especially in big projects.
That's a great overview of the visual language. Now, the book also talks about the software development lifecycle itself, different ways to actually build the software. What are the key models discussed?
Right, the life cycle.
Yeah.
The source outlines a few important ones. You've got the classic waterfall model, very linear, step by step, like a cascade. Finish one phase completely before starting the next.
Rigid.
Can be, yeah. Then there are more iterative approaches. Throwaway prototyping is where you build quick, rough versions, prototypes, just to figure out requirements or test ideas, and then you throw them away and build a real thing. And incremental development, sometimes called evolutionary prototyping. Here, you build the system piece by piece, delivering a working version early, and then adding more functionality over time.
That incremental way sounds like it delivers value much sooner.
It often does. The book points it out. You get a working system, maybe a basic version, much earlier than waterfall. But the catch is that those early increments need to be solid because they become the foundation for everything else. You can't build a skyscraper on a shaky first floor.
Makes sense. Any other life cycle models mentioned?
It also covers the spiral model, which is iterative like incremental, but adds a big focus on risk analysis in each cycle. And finally, the Unified Software Development Process, or USDP.
USDP.
Yeah, think of USDP as a framework that's also iterative and incremental. It organizes work into phases like conception, elaboration, construction, transition, and within each phase, you have multiple iterations, or mini-projects, where you build and refine parts of the system. Workflows like requirements, analysis, design, implementation, test happen in each iteration.
Iteration seems to be a common theme in the more modern approaches.
Definitely. Learning and adapting as you go.
The book also brings up performance analysis and testing quite early. Why think about those during design?
Good question. Thinking about performance early, using techniques the book mentions like queuing models, simulation, Petri nets, or real-time scheduling analysis helps you spot potential bottlenecks before you write code. It's much cheaper to fix a design than coded software.
And testing.
Same idea. The book outlines different levels. Unit testing checks the smallest pieces, like individual functions or methods. Does this one specific calculation work? Integration testing checks if those pieces work together correctly when you combine them. Does the login screen talk to the user database properly? And system testing checks the whole application against the original requirements. Does it actually do what the user needs it to do? It's often black box, meaning you test based on inputs and outputs without looking inside.
So testing isn't just something tacked on at the end.
Ideally, no. It should be planned for, and the design should make the software testable. Thinking about how you'll test influences how you design.
Okay, let's shift to some core design principles the book highlights. First up, information hiding. What's the big idea there?
Information hiding is fundamental. It's about separating the what from the how. An object should expose a clear interface, the operations others can call on it, but hide its internal data structure and the logic of how those operations are actually performed.
Well, a black box?
Kind of, yeah.
Yeah.
Think about a simple stack data structure. The interface is push and pop. You don't need to know if it's implemented internally using an array or a linked list to use it. That internal detail is hidden.
And the benefit?
Big benefits. Flexibility, mainly. You can change the internal implementation later, maybe make it more efficient, and as long as the interface stays the same, nothing else that uses a stack breaks. It reduces dependencies and makes maintenance way easier.
Got it. Makes the system less brittle. What about encapsulation? Sounds similar.
It's closely related. Encapsulation is the mechanism of bundling the data, attributes, and the methods, operations, that work on that data together within a single unit, the object or class. Information hiding is the principle of hiding the internals. Encapsulation is the technique of packaging data and methods together. As the book puts it, it raises the level of abstraction.
Okay, bundled together, internals hidden. Then there's inheritance. How does that apply in software?
Inheritance is a way to model is a kind of relationships. You define a general class, a superclass, with common attributes and behaviors, and then more specific classes, subclasses, can inherit these and add their own unique features or modify existing ones.
Like the vehicle example earlier.
Exactly. Vehicle is the superclass. Car, truck, motorcycle are subclasses. They all inherit has wheels and can move from vehicle, but then add specific things like number of doors for a car or cargo capacity for a truck. It promotes reuse and creates a clear hierarchy.
Makes sense. The source also differentiates active versus passive objects. What's that about?
This is really important for concurrent systems where multiple things happen at once. An active object has its own thread of control. It can initiate actions on its own. Think of it like an independent agent. A passive object doesn't. It just sits there holding data or providing methods. And it only does something when another object, typically an active one, calls one of its methods.
So active objects drive the action. Passive objects are used by them.
Pretty much.
And how do these objects talk to each other? The book mentions asynchronous and synchronous communication.
Right. This is about how messages are exchanged. With asynchronous communication, the sender sends a message and immediately continues with its own work. It doesn't wait for a reply, like firing off an email.
Fire and forget.
Sort of, yeah. The sender might get a reply later, but it's not blocked waiting for it. Synchronous communication is different. The sender sends a message and then waits. It blocks until the receiver processes the message and usually sends back a reply or at least an acknowledgement. Like making a phone call, you wait for the other person to pick up and respond.
Tighter coupling in synchronous, then.
Definitely. Looser coupling with asynchronous. Each has its place depending on what the system needs to do.
Okay, great foundation. Now, the book gets into reusable patterns. What are we talking about here?
Patterns are basically well-documented, proving solutions to recurring problems in software design.
Hmm.
The source talks about two main levels. Design patterns, like the ones from the famous Gang of Four book, are smaller scale. They describe solutions involving a few collaborating objects to solve a specific design issue.
Okay.
Then you have architectural patterns. These are much larger grained. They define the overall structure of a system or a major subsystem, how the big pieces fit together and communicate.
So design patterns for the details, architectural patterns for the overall structure, like choosing timber frame versus brick for a house.
That's a decent analogy, yeah.
The book also introduces component-based architecture. What's a component in this context?
A component is defined as a self-contained, replaceable part of a system that encapsulates state and behavior and offers its functionality through well-defined interfaces. Crucially, it explicitly defines both the interfaces it provides, services it offers, and the interfaces it requires, services it needs from others.
So like a building block with standard plugs and sockets.
Exactly. Usually components are designed to be independently deployable. The idea is you could build systems by assembling these pre-built or these clearly defined components. It really pushes modularity and reusability.
Okay, let's switch gears to requirements. How do we figure out what the software should actually do? The book spends a lot of time on use case modeling.
Use cases are fundamental for capturing functional requirements. They describe interactions between external users, called actors, and the system itself to achieve a specific goal. An actor isn't necessarily a person, it could be another system.
And there are different types of actors.
Yes. The primary actor is the one who initiates the use case to get value from the system. A secondary actor is something the system interacts with to complete the use case, maybe an external database or a credit card validation service. There can also be external system actors. The use case itself describes the sequence of steps, the dialogue between the actor and the system.
How do you write one? What goes into a use case description?
The source suggests a structured template. You'd have a name, a brief summary, any dependencies on other use cases, the actors involved, then the critical parts, preconditions, what must be true before starting, the main sequence, the typical successful path, alternative sequences for errors or variations, any relevant non-functional requirements like performance, the postcondition, what's true after success, and maybe a section for outstanding questions.
Very detailed. It gives the make order request example. What does that show us?
That example walks through how a customer actor interacts with an online shop system to place an order. It shows the steps: browse items, add to cart, provide shipping, provide payment, confirm order. It illustrates that flow of interaction to achieve the customer's goal.
The book also warns about making inclusion use cases too small. Why is that a problem?
Yeah, an inclusion use case is like a subroutine, a smaller piece of functionality reused by several other use cases. The warning is that if you break things down too much into tiny little inclusion use cases for every single step, you can end up with a fragmented model that's hard to follow. You lose the narrative of the user's overall goal. It's about finding the right balance.
And those non-functional requirements, performance, security, how do they fit into use cases?
They can be attached directly to the use case description they relate to. So for a login use case, you might add a non-functional requirement saying password must be encrypted, or login must complete within 2 seconds. Or if a requirement applies broadly, it might be documented separately and referenced.
It sounds like these use cases are really pivotal for everything that follows.
Oh, hugely influential. The book makes that clear. Use cases drive the analysis, help identify the objects needed, define the interactions those objects must support, guide integration testing, and even influence how you plan development increments. They're a cornerstone.
Okay, so use cases define the what. Let's go back to the structure static modeling with class diagrams. What are the key relationship types we need to know?
We touched on some already. You have basic associations, just general links, often with multiplicity like one-to-many, one customer, many orders. Then the whole part relationships. Composition, strong, part dies with the whole, like room in a building. And aggregation, weaker, part can live separately, like player on a team. Then generalization, specialization, inheritance is a kind of. And finally, dependency, which is a weaker relationship, meaning one class uses another, perhaps as a parameter or local variable, but doesn't hold a long-term structural link to it.
You mentioned multiplicities. How specific can those be?
Pretty specific. You can use numbers 1, 5, ranges, zero point 0.5, or stars for many, 0, 1. So you can say exactly 1, customers associated with 1 to many orders, 1.
The book also mentioned association classes. What problem do they solve?
Sometimes the relationship itself needs to hold data. Think about students enrolling in courses. A grade isn't really an attribute of the student alone or the course alone. It belongs to the specific enrollment linking a student to a course. An association class lets you model that enrollment link as a class itself, with its own attributes like grade or semester.
Okay. That makes sense. And constraints.
Constraints are just rules that need to hold true in the model. You might write them in curly braces like this on the diagram. For example, on an account class, you might have a constraint balance.
The source differentiates modeling the problem domain versus the software system context. What's the focus of each?
Modeling the problem domain is about capturing the real-world things the software deals with: customers, products, invoices. These often become your core entity classes, the data the system manages. Modeling the software system context is about defining the boundary between your software and everything outside it: hardware devices, other software systems, human users, actors, timers. These become external classes, often stereotyped as input device, output device, user interface, etc., to show how the system interacts with its environment.
Got it. Domain is the what it's about. Context is the where it lives and who it talks to.
Right.
Once we have that static picture, how do we categorize the objects inside the system? The book talks about object structuring.
Right. Object structuring helps organize the design by assigning rules to objects. The book suggests categories like boundary objects handle communication with the outside world, user interfaces, device interfaces, system interfaces. Entity objects represent the core data, usually persistent information. Control objects manage the flow of logic within a use case, coordinating other objects, and application logic objects contain the business rules, algorithms, or specific services.
Can you give examples, like for an online bank?
Sure, a boundary object might be the web login form or maybe an ATM interface. An entity object would be customer account or transaction record. A control object could be fund transfer controller that orchestrates the steps of moving money. And an application logic object might be a interest calculation service or a fraud detection rule engine. The book actually further refines application logic into things like business logic, service algorithm, coordinator objects too.
Okay, that clarifies the roles. How do we show these dynamic interaction modeling?
This brings us back to communication diagrams and sequence diagrams. Both show objects collaborating by sending messages to fulfill a use case. Communication diagrams emphasize the links, the pathways between objects, using numbers to show message sequence. Sequence diagrams emphasize the time ordering, using vertical lifelines for objects and horizontal arrows for messages.
And the difference between analysis and design focus here.
In analysis, you're mainly focused on what information needs to pass between objects. Send customer details. In design, you get more specific about how, which exact operation method is called. Is it synchronous, wait for reply, or asynchronous, send and continue? You're defining the concrete mechanisms.
The book uses the make order request use case again with a communication diagram. What does that show?
It maps out the players, maybe a customer UI object, an order coordinator object, an inventory service object, a payment service object, and draws a line showing who sends what message to whom in what order to process that order request. It visualizes the collaboration.
And this distinction between state-dependent and stateless dynamic modeling.
Stateless modeling is fine when an object always responds the same way to a message, regardless of its history. State-dependent modeling is needed when an object's current state dictates how it behaves, what messages it accepts, what it does, what state it transitions to next. If an object has significant states, you need to model that.
Which leads us to state-machine modeling. What are the basics here?
State-machine diagrams, state charts, model the life cycle of a single object. You have states, rounded boxes representing a condition or situation. You have transitions, arrows between states, triggered by events. Transitions can have guard conditions, a Boolean check that must be true for the transition to fire, and actions, things that happen during the transition.
So state, event, condition, action, can these get complex?
They can. That's why the book mentions hierarchical state charts. You can have composite states that contain nested substates. This helps manage complexity. You can zoom in or out. You can also define transitions coming out of a composite state that apply to all its substates, which simplifies things.
The ATM example helps visualize this.
Yeah, the ATM control state chart shows states like idle, waiting for card, validating PN, selecting transaction, dispensing cash. Events are things like card inserted, PN entered, amount selected. Actions might be display welcome message, eject card. It maps out the ATM's behavior flow.
And how does this connect back to the interaction diagrams, state-dependent dynamic interaction modeling?
This means the state chart governs the interactions shown in a communication or sequence diagram. Using the validate PIN example, the ATM control object's current state, e.g. waiting for PN, determines whether it will accept a PN entered message and what it does next, as shown in the interaction diagram for that use case. The state chart acts like the rulebook for the interaction.
Okay, we've gone from diagrams to life cycles, principles, patterns, objects, interactions, states. Let's zoom way out now to software architecture. How does the book define this?
Software architecture is defined as the fundamental organization of a system. It's about the major components, how they relate to each other, and the environment, and the principles guiding the system's design and evolution. It's the high-level blueprint. The book also specifically mentions component-based software architecture, focusing on building systems from those independent components we discussed.
And the idea of multiple views.
Right.
Yeah.
You can't usually capture everything important about an architecture in one picture. So you use multiple views. The source mentions the static view, components, connectors, structure, the dynamic view, runtime interactions, collaborations, and the deployment view, how software maps to hardware. Different views for different stakeholders and concerns.
Like different architectural drawings for building floor plans, electrical, plumbing.
Exactly. And the book revisits software architectural patterns. What are some examples of these big picture patterns?
Well, for structure, there's the layers of abstraction pattern. Think of networking protocols like the TCP/IP stack. Each layer provides services to the one above it and uses services from the one below. For communication, patterns include call return, typical sequential flow, asynchronous message communication, good for decoupling, like message queues, and synchronous message communication with reply, common in client-server. The book mentions styles like client-server, SOA, etc., which we'll get to. But first, software quality attributes. Why are these so vital at the architecture level?
These are the non-functional requirements.
Right.
Maintainability, modifiability, testability, scalability, reusability, performance, availability, security, and so on. Architectural decisions have the biggest impact on whether you can achieve these qualities. Choosing a monolithic versus a microservices architecture, for instance, drastically affects scalability and modifiability. You have to design for these qualities from the start.
Okay, so how do we bridge the gap from architecture to detailed design? Software subsystem architectural design.
This is about breaking the system down into manageable chunks, subsystems. The key principle here is separation of concerns. Group related things together, separate unrelated things.
What criteria guide that separation?
The source is just a few. Functional relatedness, group things supporting the same features, information hiding, create subsystems around key data or resources, sometimes geographical location if parts are physically distributed, or control, grouping based on coordination responsibility.
Being common types of subsystems?
Things like a dedicated user interface subsystem, a data management subsystem, maybe a process control subsystem for real-time aspects, or a central control subsystem for orchestrating business logic.
Right. Now, into specific architectural styles, designing object-oriented software architectures. What core OO concepts are emphasized here?
It really comes back to the basics: information hiding, defining clear class interfaces and operations, methods, using inheritance effectively, understanding objects as interacting instances. The dynamic models, sequence communication diagrams, heavily influence the design of the class operations.
The book mentions state machine classes. How do they help?
Instead of coding state logic directly into every stateful object, a state machine class encapsulates that transition logic. You could potentially reuse this class, configuring it with the specific states and transitions for different kinds of objects. It promotes reuse and separates the state management concern. The ATM example again illustrates this.
And abstract classes.
Abstract classes are templates. You can't create direct instances of them. They define a common interface, maybe some implemented methods, but also abstract operations methods declared but not implemented. Subclasses must provide implementations for those abstract operations. It's great for defining a common framework while allowing variations. The checking account savings account example is classic.
Okay, moving to a very common style. Client-server software architectures. What are the typical patterns?
The most basic is multiple client single service. Lots of clients talking to one server. But you also see multiple clients, multiple services, and multi-tier architectures, where you have intermediate layers, like a business logic layer between the web server and the database. Communication is often synchronous call return or synchronous message communication with reply.
What about client and service proxies and middleware?
In distributed systems, proxies hide the network complexity. A client proxy looks like the remote service but runs locally. It handles sending the request. A service proxy on the server receives the request and calls the real service. Middleware provides the plumbing, the communication protocols and services that make this distributed communication easier. Examples mentioned include RPC, RMI, COM, Corba technologies that help objects on different machines talk to each other.
And mapping objects to databases comes up here too.
Yeah, because client-server systems often need persistent data storage, typically in relational databases. So you need strategies for mapping your object model, classes, inheritance associations, to database tables, columns, primary keys, and foreign keys.
Next up, designing service-oriented architectures, SOA. What defines SOA according to the source?
SOA is about building applications from distributed, autonomous services. Key ideas are loose coupling. Services don't need to know much about each other's internals. Reusability, services can be used in multiple contexts. And interaction via well-defined interfaces, often using standard protocols like web services. It promotes flexibility and scalability.
How do services find each other? The broker patterns.
Right. A broker acts like a directory. Services register themselves with the broker. Clients discover services by querying the broker. The broker handles the brokering, connecting the client to the provider, sometimes staying in the communication path, sometimes just providing the address.
And transaction patterns like two-phase commit, why are they needed?
Because a single business action might involve multiple independent services. If you transfer money, you need to debit one account service and credit another. Two-phase commit helps ensure that either both services succeed or both fail, rollback, maintaining data consistency across services. It's crucial for reliability in distributed systems. The book also mentions patterns for more complex or long-running transactions.
What about negotiation patterns?
These handle cases where a client and service might need to agree on terms before interaction, like quality of service levels or specific DIA formats.
The online shopping example illustrates this.
Yes, it shows how an order service might interact with an inventory service and a delivery service. Each is independent, loosely coupled, communicating via messages to fulfill the overall shopping function. It highlights that service collaboration.
Okay, then, designing component-based software architectures. What are the key design points beyond just defining components?
It's about how you structure these components, how they connect via ports, interaction points, and connectors, the communication links, deployment strategies, and managing dependencies. The book talks about component structuring criteria and communication patterns suitable for components, like broadcast or subscription notification, often called publish-subscribe.
The emergency monitoring system deployment example shows.
It shows how different software components, like alarm handler, sensor reader, database logger, might be physically deployed onto different hardware nodes in a distributed monitoring system, communicating over a network. It emphasizes the modularity and deployability aspects.
Now for a specialized area, designing real-time software architectures. What's critical here?
Time. Real-time systems have strict timing constraints. They must respond to events within deadlines. So concurrency is key, managing many things happening seemingly at once. Design focuses on concurrent task structuring, breaking the system into independent tasks, processes, or threads. The book classifies tasks: periodic, event-driven, I/O, control, etc.
And how do these time-critical tasks communicate?
Communication needs to be predictable. Both asynchronous and synchronous methods are used, but the choice heavily depends on timing needs and avoiding issues like priority inversion. Formal specifications like Task Interface Specification, TIS, and Task Behavior Specification, TBS, help define and analyze task interactions and timing.
The automated guided vehicle, AGV, example.
It shows how an AGV controller might be built from tasks like navigation, motor control, sensor processing, communicating via messages to ensure the vehicle operates safely and efficiently within its required time constraints.
Last, architectural style. Designing software product line architectures, SPLs. What's the unique focus here?
SPLs are about efficiency for building a family of related products. The focus is on commonality, what all products share, and variability, where they differ. Feature modeling is used alongside use cases to explicitly model these variations. The architecture itself is designed to support this variability, often having a core platform with plug-in points for different features.
How does component-based development help SPLs?
It's a natural fit. You could develop reusable components for common functionalities and specific variant components for the differences. Using well-defined interfaces, plug-compatible components, makes it easier to assemble different product configurations from the available component set.
Okay, we've toured a lot of architecture. The book circles back to software quality attributes. Why the final emphasis?
To reinforce that these qualities, maintainability, modifiability, testability, traceability, scalability, reusability, performance, availability, security, are not afterthoughts. They must drive architectural decisions. The book links these back to the comment method, which it details elsewhere, and gives examples, like how the banking system uses encryption for security or distribution for scalability. Achieving these qualities is a primary goal of good architecture.
And finally, the case studies and the catalog of software architectural patterns in the appendices. How valuable are these?
Extremely valuable. The case studies, banking, online shopping, emergency monitoring, AGV, show how all these concepts come together in realistic scenarios. You see the trade-offs made. The pattern catalog is a fantastic reference. It provides a template for describing patterns, context, problem, solution, strengths, weaknesses, etc. It covers layers, client, server, broker, publisher, subscriber, patterns for concurrency, distribution, and more. Yeah, the catalog is like a practical toolkit. You can look up patterns relevant to the specific problems you're facing in your own designs. It's a great resource for learning from established solutions.
So, wrapping up this deep dive into Goma's software modeling and design, the big takeaway seems to be that building good software requires structure, planning, and a shared language. It's about using notations like UML, understanding different life cycles, applying solid design principles, leveraging patterns, and always keeping those quality attributes in mind. It's about creating blueprints for complexity.
Absolutely. It's a comprehensive look at how to approach software design thoughtfully. And while we've covered the highlights, there's so much more depth in the source itself. We really encourage you, the listener, to dive into the book for areas that particularly interest you or relate to your work.
Right. And here's a final thought to leave you with. Even if you're not writing code day to day, think about these principles. Modularity, clear interfaces, separating concerns, managing complexity through structure, considering different viewpoints. How might these ideas from software design apply to problems or systems you work with in your own field? Are there parallels in how you organize projects, design processes, or even structure arguments?
That's a great point. These concepts for tackling complexity often translate surprisingly well across different domains, something to definitely reflect on.
We hope this deep dive gave you a solid framework for understanding software modeling and design. Let us know your thoughts or any questions that came up. Keep exploring, keep learning, and we'll catch you on the next deep dive.